Welcome to another Great Cow Basic demonstration stroke tutorial for the PIC16F171 chip family. Hello, my name is Venn. I'm a co-developer of Great Cow Basic along with a whole team of other people. But if you do like these videos and they are useful to you, press the thumbs up down below in the comments. So let's get into the PowerPoint and just touch on the subjects we'll be looking at. So today we're looking at tutorial 12, which is using EEProm, showing the values of the EEProm that we're going to write to it on a serial terminal and other software. We're going to use two bits of software today, the terminal and another. What am I using for this? I'm using the microchip low pin count demo board. I was going to pick up one of them, but you can make your own on breadboard, and Chris Roper from South Africa has put a layout there for you, and we're just going to hook into that layout. So whatever we do on the breadboard, we can do on the actual physical board. That's that green thing on the left. So this is the layout. I will always leave this here for 4 seconds so that you can copy that out and use that. Great. So what is EEProm? EEProm is electrically erasable read-only memory. It's a type that is non-volatile. That means it's there for the long term. It's used across a whole series of computers in your mobile phone, and it's integrated into these microcontrollers, and it's there for the long-term storage of a relatively small amount of data. But it's extremely useful because you can then recall that at any time, and it's not erased in the same way as RAM is. So it is for there for the long term. Let's have a think about, so how much is in this chip? This chip actually has 256 bytes, typical. That's quite typical. 128 is also typical. I've seen chips with 1K, that's 1024, and 2K, 2048, 2048 bytes. And the thing is that in Great Cow Basic, that's exposed through a system constant called chip EEProm. And we'll look at that when we go into the code. And so, summary, EEProm there for the long term, and this particular chip's got 256 bytes. So today what we're going to do is hook up the serial terminal. So a recap, connect up the ground and the TX to the USB TTL device on port C4, and we've covered that off in previous, and that hasn't changed, but we will recap that in the code. So what we're going to do is we're going to actually write some EEProm, and we're going to read some EEProm. And it's extremely simple. Essentially, we have two commands. The top one, which is EEPWrite, and EEPRead. These were defined maybe 10 years ago by Hugh, the original developer, and what you send it is an address. That's a pointer to the EEPROM itself. That could be 0 to 256 in this particular chip, and you say what byte data do you want to send out. And then the inverse of that EEPRead is you send it an address and then in data so that you can actually bring the data in. And we're going to look at that in terms of on a serial terminal to see what results we're getting. I'm going to show you one way of doing it, but there's another way. And you can write table data in Great Cow Basic as shown in the top right-hand corner here in the program. I'll just put a pen mark against it eventually. There we go here at the top. You can actually write table data out. And what you do is you define a table, give it a name, and then you say store data. And store data means write it to EEPROM. And in this particular case, we've written 6 values, and you can see 6 values are actually being input into EEPROM for you. So we can use EEPWrite, EEPRead, or we can use table data. Today, we're going to use EEPWrite and EEPRead. So what are we going to cover off? We're going to look at the sample code. We're going to set up the PPS so that we can read and write via the terminal. We're going to write some values, read some values, and show the results on that terminal. Then we're going to do the same, but this time we're going to actually use PICKitPlus to actually see the results because it's quite dynamic that way. So let's get into some code. My desktop, GCStudio. I enter GCStudio to enter the software. I'll be doing some other work, so I'm going to make sure I select the right folder. Here it is, 17126 chip range. Click, and in we go. And we're inside of the editor. So I'm going to zoom in for you. If I click on it, it would help. There we go. We have a list of files on the left. I'm just going to do exactly what I do every time. Control F.gcb, turn the filter on, and now I can see a list. This time we're going to use 160 and 165. We might touch on the table EEProm as well. 160 showing EEProm data to serial terminal, and we'll bring up 165 and put that in the IDE also. Then I'm going to close down the Explorer. This is zoom in a bit further for you. Now we can see we've got the same as before. We've got our hash chip and our option explicit. And then we've got the PPS. We must set up the PPS for the serial output. So we're going to delete that so we can recreate it and learn that process. I'm pressing function key F4 to bring up the menu of options. But you can also press in the top right hand corner up here, there's a little icon with show task menu, same option. PPS tool. I've selected PPS tool and it's loaded up the PPS tool. You can see that on the screen. I've selected the correct chip. I use the drop down, which you cannot see. So I'm going to change my zoom and bring that into position. Select TX1, port RC4, which is port C.4, and add it in. It's created a listing for my PPS. I copy that into my cut and paste buffer, press OK, and then go back into my code and paste it in. And it set up the PPS for serial. We can see that later on. So, what have we got? No change to our little diagram here because we've got port C.4 as TX and the LEDs, etc. But we're just going to be writing out to the EEProm the same constants as previously. We've seen this before, which is important. Set up the serial port. Set up the baud rate. Transmit blocking to ensure that it sends out all the bits before it sends the next bit and with no delay. Let's recap US art baud rate. That needs to match my terminal. So if I actually use a little drop down here, I can select the terminal in here. There's a terminal, but it's also on function key F9. It starts up the terminal, which is on the screen there, which is great. Let me just change the zoom slightly. Now you can see the terminal because it's live. It's integrated into the editor. I'll just shut that down for a moment. Let me just, as I said, recap this. If I comment out the baud rate, you will get an error message because the compiler knows that you need to have a baud rate. So if I compile that, just as a test and demonstration, I will get an error. And it will say US Art1 setup incorrect, no baud rate specified, missing US Art setup. So it tells you that you've got an error. Just restore the baud rate and recompile. And now we get a program that's compiled. Wonderful. So let's look at our program. The classic do forever loop. We've got some display here. Now we know what to expect because this is just the layout on the terminal. And so most of this in the first preamble here is setting up the screen for us on the terminal. And if we remember from the PowerPoint, what that looks like is essentially a table of the EEProm. Then what I'm going to do is set my out data to a value of 255 minus the EEProm address. So where's that coming from? Well, there's a for next loop here. EEProm address is 0 to the constant of chip EEProm minus 1. So we already know that that's going to be 0 to 255 now. But let's verify that. Look at our tasks that we can run. Pick info. Open up Pick info. And if we look inside for this particular chip, we can see that we've got EEProm at 256 bytes. EEProm is exposed as chip EEProm. And you can see other parameters in here as well. But clearly we just need to make sure that we don't go beyond the extremes of 256. So we do that by 0 to minus 1. There we go. Back to our program. So what I'm going to do is I'm going to set the out data to 255 minus the value of EEProm address, which will be 0 initially. And so this will write to it will write a range of 0 to 255. And here is the actual work. EP write to that EEProm address, the out data, which we previously set. I set the in data to 0 because I want to show that on the screen. Don't use the same variable because it might not actually read it. So in data is the incoming data, and then we print it on the screen. So if the out data equals the in data, then print that on the screen, else print out 2 dashes. It could be 2 exclamation marks. I don't care. It's just the way it's going to format. So let's bring up terminal again and put that on the screen. I'm going to connect to my serial port. It's now active. I'm going to press hex, make hex and flash. It's now programmed it. And on the terminal, we see a display. And that display is what we've written. It's written FF, FE, because as we increment through, we get a result. Now, this could be erroneous. It could be. It might not be though. So what we're going to do is I'm just going to prove to you that this is not in error, because we can change our values here. I'm going to change the out data in the source code to 55, and then reprogram it. We will see a little bit of serial chatter in the terminal. It's quite typical. And now, after a few seconds, it will write 055 hex. There we go. And you can write random data if you wish, just to test it all out. Because with random data, it's a little bit harder to prove that it's actually working. There we go. So what I'm going to do now is write out the out data. So it will be the value of FF to all the way through to 0, and this is 256 bytes, and then we're going to validate this now using an external piece of software. Great. Select the task menu. I'm going to use PICKitPlus because that's what I've got installed. You could use your own program of choice. And if we look at this, we can see we've got the right chip selected up here. I'm going to turn off read the program memory, just read the EEProm memory at the bottom. Okay, I'm going to read that in. And if we look, we get the same values. We've got FF through to 00, exactly the same as we had on the screen. Let's change my source program to 255 to 55 hex in the background. We'll let that program in the background, and then once it's completed, I'm going to read it. So we can see, oh, there we go. It hasn't completed the write, of course. As we can see, we've got 55 hex all the way through now. So we can now write any values we like. We can create strings. We can write strings out there, read strings. We can do anything we like using EPRead and EPWrite. Let's go back to the IDE, and we're just going to bring up .165, showing EEProm table value. So here we have table data, the same setup in terms of all the PPS, etc. Oh, documentation's wrong. Need to get that right, don't we? Let's just update my documentation. There we go. TX4. What we're doing in here is a slightly different method. We're using a table. So I've defined a table of values 1 through to 7. So that's 1, 2, 3, 4, 5, 6, 7 values. And I'm going to write that to the EEProm. I can do that by using the table data source, and I say store that data, and it will write that out to EEProm. And how do I do that? I just read the table. I need to read one value just to initialize it, read the table, tell it which data source it is, tell it the location, and write out some variable. And I'm then going to update EPWrite location 8 with the value of 55. So I'm going to write it, or automatically write out this table data, and then in the 8th position, I'm going to write 55. Program it. Now this time, I'm just going to use PICKit2 because I can see it much quicker in here. So I'm just going to read that value. And here we have the value of 1, 2, 3, 4, 5, 6, 7, and 55. Absolutely correct. So what is this number here? When you write it out using this method, it tells you how many values are in the table. And it says there are 7 values in your table, which is absolutely correct. And then I've written out my favorite value of 55 into the EEProm. So what this shows is that using EEProm with Great Cloud Basic is extremely easy. It comes down to EPWrite, EPRead. Get back to PowerPoint. So we've used EEProm, we've used serial, I2C, we've used PMW, we've used timers, inputs and outputs. So now what we're going to do tomorrow is look at some using the I2C that we set up yesterday in the previous tutorial. We're going to put some graphics out to that, to the GLC display, and then we're going to change complete protocol to SPI, and then we're going to wrap up with a whole series of other pieces of information and technology. So with that, we'll call it a wrap.